So look at the problem I have shown on the screen. So I am going to discuss a problem based on the work energy theorem. Before I go for the next concept, I would like to first discuss here two problems based on work energy theorem. Already discussed one problem in the end of the previous class. So look at the problem number 5 on the screen. I will once read out the problem. What work should be performed by an external agent to increase the velocity of a body of mass 2 kg from 2 meter per second to 4 meter per second in a distance of 5 meters? There are three parts in the question. First part question, along a smooth horizontal floor. Then second part of the question, along a horizontal floor, if a constant retarding force of magnitude 2 Newton acts for the entire distance. Third part of the question, up along the inclined surface, nu equal to 0.2. That means equation of friction between the body and the inclined surface is 0.2. Of a fixed inclined plane of angle of inclination 37 degrees to the horizontal. Take g equal to 10 meter per second square and sine 37 degrees equal to 3 by 5. So I am going to discuss this problem. In case you want to try this problem yourself first, you can take a pause and try it yourself. Otherwise, look at the solution which I am going to discuss now. So here you are given the initial velocity of the body as 2 meter per second, which is denoted by u. Final velocity of the body after traveling 5 meter distance is given as 4 meter per second. The mass of the body is given as 2 kg. So in the first part of the question, the body is moved in the smooth horizontal surface. Let capital F denote the magnitude of the force applied by an external agent which gives acceleration to the body, which acts in the direction of the motion. So the weight mg of the body acts vertically downwards. The normal reaction force on the body by the surface in contact acts vertically upwards perpendicular to surface in contact and directed away from surface in contact. According to the work energy theorem, the change in the kinetic energy of the body is equal to the total work done by all the external force acting on the body. So change in the kinetic energy of the body is equal to work done by all the external force acting on the body. That is work done by the force applied by the agent plus work done by the gravitational force on the body plus work done by the normal reaction force. Here W subscript N represents the work done by the normal reaction force on the body. W subscript small g represents work done by the gravitational force on the body. W subscript small a represents work done by the external agent of the body. So change in the kinetic energy of the body is equal to final kinetic energy of the body minus initial kinetic energy of the body. You can write half m into v square minus u square. Work done by the gravitational force of the body is 0 because the gravitational force acts perpendicular to the displacement. The body is moved in the horizontal direction. The displacement of the body is directed in the horizontal direction. Gravitational force mg acts in the vertical direction. Work done by the normal reaction force on the body by the surface in contact is also 0 because the normal reaction force acts perpendicular to the direction of the displacement of the body. So work done by the agent of the body is equal to half m into v square minus u square. So the mass m is given to be 2 kg. The magnitude of the final velocity is 4 meter per second. The magnitude of the initial velocity is 2 meter per second. Can simplify this. So work done by the agent in the body will be equal to the first part of the question. $12 joules. So for first part of the question, answer is 12 joules. If you want to copy the working, you can take a pause and copy this working. So now coming to the second part of the question. Here in the second part of the question, you are asked to find work done by the external agent to increase the velocity of the body from 2 meter per second to 4 meter per second in distance of 5 meters along a horizontal floor if a constant retarding force due to friction with magnitude 2 Newton acts for the entire distance. Let small f denote the magnitude of retarding force due to friction. So in the second part of the question, also we follow the same principle, that is work energy theorem. But in the second part of the question, the body is moving on a horizontal surface which exerts a constant retarding force. Small f is the magnitude of the retarding force due to friction, which opposes the motion of the body. Again, applying the work energy theorem, the change in the kinetic energy of the body is equal to total work done by all the external force acting on the body. So delta Ke represents change in the kinetic energy of the body is equal to work done by all the force, that is work done by the external agent plus work done by gravitational force plus work done by normal reaction force plus work done by force of friction. Here W subscript small f represents the work done by the frictional force in the body. The force of friction acts opposite to the direction of the displacement and has a constant magnitude equal to 2 Newton. So work done by the frictional force of the body can write Fs cos theta. Force of friction acts opposite to the direction of displacement, therefore the angle between force of friction and direction of the frictional force on the body and direction of displacement of the body is 180 degrees. So you get this as work done by agent minus Fs. So work done by the external agent on the body can carry this term to the right side, other side. Work done by the external agent of the body equal half m into v square minus v square plus F into S. F is the magnitude of the retarding force and S is the magnitude of the displacement. So magnitude of the retarding force equal to 2 Newton. Magnitude of the displacement equal to 5 meter. Don't make corrections for what you have already copied for the solution of the first problem. This must be written separately. Again, m equal to kg, u is 2 meter per second and v is 4 meter per second. And small f is 2 Newton, s is 5 meters. So 12 joules plus 10 joules. So for second part to the question, you get the answer as 22 joules. Come on, copy down the working for the second part of the question. In case you need more time to copy this working, you can take a pause and copy the working. Next, I am going to discuss the third part of the question. So in the third part question, you are asked to calculate the work done by the external agent on the body to increase the velocity of the body from 2 meter per second to 4 meter per second up an inclined surface of a fixed inclined plane of angle of inclination 37 degrees to the horizontal. The coefficient of friction between the block body and the inclined surface is 0.2. So let us consider the force acting on the body here, free body diagram of the body. We'll apply same principle again, changing the kinetic of the body equal total work done by all the forces. Further, you have to estimate the magnitude of the retarding force on the body. Magnitude of the work done according to the work energy theorem, changing the kinetic of the body is equal to work done by the resultant force of the body. To calculate work done by the resultant force, again you can follow any one of the two methods. One method is first find the magnitude of the resultant force on the body by the free body diagram technique. Then work done by the resultant force, you can write product of the magnitude of the resultant force and displacement. That is one method. The other method is you can calculate work done by individual forces separately. The gravitational force mg acts vertically downwards, perpendicular horizontal base of the inclined plane. N is the magnitude of normal reaction force on the body by the inclined surface, which acts perpendicular to the inclined surface and directed away from the inclined surface. So the body is moving up along the inclined surface in this case. Therefore, force of kinetic friction or sliding friction acts opposite to the direction of the motion of the body. So you can resolve the weight mg into rectangular components. Parallel to and perpendicular to the inclined surface. As usual, we choose the direction of the motion up along the inclined surface as positive direction of x-axis. So the component mg cos theta acts perpendicular to the inclined surface. The component mg sin theta acts down the inclined plane parallel to the inclined surface. Let capital F subscript A represent magnitude of the force applied by the agent on the body, which acts in the direction of the motion. Again, applying the work energy theorem. Consider changing the kinetic of the body equal total work done by all the force acting on the body. So I choose the direction perpendicular to the inclined surface as y-axis. Here N is the magnitude of the normal reaction force on the body by the inclined surface, which acts parallel to y-axis in the positive direction of y-axis. The component mg cos theta acts opposite to normal reaction, the negative direction of axis. Therefore, a y component of resultant force in the body is given by phi equal to n minus mg cos theta. So in this case, the body has no motion parallel to y direction. Therefore, y component of resultant force of the body has to be 0. So magnitude of normal reaction of the body is equal to mg cos theta. So the force of friction, not Fk, is equal to nu into N. Nu is the coefficient of friction between the block and the inclined surface. That is nu mg cos theta. According to the work energy theorem, the change in the kinetic energy of the body is equal to total work done by all the forces acting on the body. That is work done by the force applied by the agent. Here W subscript A represents work done by the force applied by the agent on the body, plus work done by the force of friction, plus work done by the gravitational force on the body, plus work done by the normal reaction force on the body. Here Wn represents work done by the normal reaction force of the body. W subscript G represents work done by the gravitational force of the body. W subscript F represents work done by the frictional force on the body. Delta K represents change in the kinetic of the body, which you can write half m into v square minus u square. You have to calculate work done by the agent of the body. The force of friction acts opposite to the direction of the displacement. So work done by the constant retarding force due to friction can be done minus Fk into S. As I discussed earlier on how to calculate work done by the gravitational force of the body. You can resolve the gravitational force mg into two rectangular components. One component parallel displacement, another component perpendicular displacement. The mg can be resolved into components parallel to and perpendicular to the direction of the displacement. The component mg cos theta acts perpendicular to the direction of the displacement of the body. The component mg sin theta acts parallel to the displacement and in a direction opposite to the displacement. That means component mg sin theta is opposite to the direction of displacement. The component mg cos theta is perpendicular to displacement. Therefore, need not consider the component mg cos theta for calculation of work done. So work done by the gravitational force of the body can be written as, because the component mg sin theta acts opposite displacement, work done by the gravitational force of the body can write minus mg sin theta into S. Work done by normal reaction for the body is 0. You can arrive at the same conclusion another way also. Work in general, when the center of gravity of the body rises through a vertical height h near the earth's surface, work done by the gravitational force of the body can be done minus mgh. H is the vertical height through which the body rises. So if f is the magnitude of the displacement parallel to the inclined surface, and h is the vertical height, corresponding vertical height through the center of mass of the body rises, then we can write sin theta equal to h by s. Theta is the angle of inclination of the inclined plane to the horizontal. Or h can be written as f into sin theta, which we have written here. So work done by the force applied by, you can solve for WA. WA is the work done by the force applied by the agent of the body, which you are asked to find. So work done by the force applied by the agent of the body can be written as half m into v square over s square plus Fk into S plus mgs into sin theta. Fk equal to nu into mg cos theta. Nu is given to be 0.2. M is 2 kg. G is 10 meter per second square. Cos theta, cos 37 degrees 4 by 5. This you can simplify it. That comes out to be 3.2 newtons. Can copy down the working now, because the rest of the part of the discussion is only simplification. You have to simply substitute the numericals and simplify it, that you can do it yourself. Come on, copy down the working. We are substituting all the values in SI units. So work will be in joules. Sine 37 degrees equal to 3 by 5. Solve this. You can try to simplify this yourself. Come on, copy on the working. Don't wait for me to complete the simplification. You can try to do the simplification yourself. So you get the answer as 88 joules. For third part question. In case you need more time to copy this working, you can take a pause and take your own time. So next I am going to discuss about conservative and non-conservative forces. Before I discuss about conservation of energy, I'd like to first discuss about conservative and non-conservative forces. So here, conservative force. First we'll discuss the term conservative force. Now when the body is suppose displaced from one position A to another position B, then again displaced back to the initial position. That means the body moves from one position A to another position B and then again travels back to the initial position. We say that the body has completed round trip. So before we discuss the concept of potential energy, it will be necessary to discuss about the conservative forces. So far I have discussed about the terms work, power and kinetic energy, and also about the work energy theorem. So before I discuss the term potential energy, I would like to first discuss this term conservative forces. So when the body is displaced from one position A to another position B along some path, and then the body returns back from B to the initial position A, we can say that the body has completed a round trip. So work done by any one of the forces acting on the body for the round trip can witness work done by the force on the body when it displaced from position A to the position B, plus work done by the force on the body when it displaced back from B to A. So in general, when a body is displaced from one position A to another position B, then next it travels back from B to A. Then we can say that the body has completed a round trip. So work done by a force on the body for round trip can be written as work done by the force for displacement from A to B, plus work done by the force on the body for displacement from B to A. So work done, if the work done by the force on the body for round trip is 0, then the force is said to be conservative. For example, the body is projected from surface of the ground, surface of the earth, vertically upward with some initial velocity, so that it moves from one position A to another position B at some height h above this position A. Then let us suppose it travels back. That means falls under gravity from B to A. Let h denote the vertical height to which the body rises as it moves from A to B. So during the upward motion, the gravitational force mg acts opposite to the direction of the displacement. So work done by the gravitational force of the body. When the body moves from A to B, you can write mgs cos theta. Theta is 180 degrees. The gravitational force mg acts opposite to the direction of the. Here U is the initial aspect projection. Opposite direction of displacement. So work done by the gravitational force of the body can be done minus mgh, provided this height h is negligibly small compared to radius of the earth. But when the body is moving downwards from B to A, if you consider the downward motion separately, when it is moving from B to A, the gravitational force mg acts in the direction of the motion or in the direction of the displacement of the body. So work done by the gravitational force of the body when it moves back from B to A can be done plus mgh. So work done by the gravitational force of the body when it completes a round trip and returns to the starting position A will be 0. So at the elementary level, we can say that the force is conservative if the work done by the force on the body when the body completes a round trip is 0. Force of gravity is an example for conservative force. Other examples for conservative force are elastic force exerted by an ideal spring. Later when I discuss about elastic potential energy, I will be discussing how the work done by the elastic force by a spring on a mass connected to one end of spring becomes 0 when the mass completes a round trip. And work done by the Coulomb electrical force in the same way. And a charged particle, when the charged particle completes a round trip in the electric field will be 0. That means force of gravity is an example for conservative force. Elastic force by an ideal spring which obeys Hooke's law is also an example for conservative force. The Coulomb electrical forces between two charges or static charges can also be considered as an example for conservative forces. So all such forces which arise due to the intrinsic interactions between the body and the nature are usually conservative. So work done by conservative force on the body when the body completes a round trip is 0. So you can say that a force is non-conservative if the work done by the force on the body when the body completes a round trip is not 0. For example, if there is air resistance, in the same example I was talking about, let us suppose the body is projected upwards from the position A with initial velocity U. So it moves from A to B and then again moves back from B to A. If there is viscous force due to air, the opposing force or retarding force due to air or viscous force due to air we call air resistance, which always acts opposite to the direction of the velocity. So when the body is moving from A to B, work done by air resistance on the body for motion from A to B is negative, because when the body is moving from A to B in the upward direction, air resistance acts downwards. So when you consider the motions from B to A separately, when the body is moving from B to A in the downward direction, the air resistance acts upwards again opposing the motion of the body. Again the air resistance acts opposite to the displacement of the body for motion from B to A. So work done by the A resistance of the body for motion from B to A is also negative. So total work done by the A resistance on the body when the body completes a round trip from A to B and back to A will be equal to WAB plus WBA. Both are negative means sum cannot be zero. The sum is again negative. So A resistance is an example for non-conservative force. So when a body slides on a rough surface, the force work done by the force of sliding friction on the body will not be zero in the body. Suppose if a block is projected up along the inclined surface of a fixed inclined plane with some angle of inclination theta to the horizontal, and let A denote the initial position of the body near the bottom of the inclined plane. Let B be the highest position up to which the block moves along the inclined plane, at which velocity becomes zero. Let H denote the maximum vertical height through which the body rises above the initial position A. Then the body is sliding up along the inclined surface. The force of kinetic friction on the block by the inclined surface acts down the inclined plane. So I am going to discuss the calculation of work done by the frictional force on the block for the round trip. So work done by friction force on the block when it moves from A to B will be, suppose if the coefficient of friction between the block and the inclined surface is constant throughout the motion of the block on the inclined surface, that means the inclined plane is equally rough or uniformly rough between A and B, so that coefficient of friction between the block and inclined surface has same value throughout the motion from A to B. Then magnitude of kinetic friction on the block by the inclined plane can be assumed to be constant during the motion, which is given by nu k into n. Magnitude of normal reaction of the block will be equal to mg cos theta. So work done by the frictional force of the block when it moves from A to B will be equal to Fk into F into cos 180 degrees, because force of kinetic friction acts opposite direction of the displacement of the block. When the block is sliding up the inclined plane, force of kinetic friction of the block acts down the inclined plane. So work done by the frictional force of the block will be equal to minus nu k mg cos infinity F. Here F is the magnitude of the displacement of the block for motion from A to B. F is the magnitude of the displacement of the block for a motion from A to B, or distance the block moves up along the inclined surface before its velocity momentarily becomes zero. If tan theta is greater than the coefficient of friction between the block and the inclined surface, then the block will again slide back to the bottom. So work done by the friction force in the block when it's sliding back to the bottom. When the block is sliding down the inclined plane, direction of the friction, I mean kinetic friction on the block or sliding friction on the block by the inclined plane, will be up the inclined surface. That is, again it will be opposite to the direction of the displacement. So when the displacement is for motion down the inclined plane from B to A, force of kinetic friction acts up the inclined surface. Again opposite to the motion. So work done by the force of friction on the block for motion from B to A will minus nu k into mg cos infinity F, again negative. So total work done by friction for the block for the round trip is not zero. So force of friction is an example for non-conservative force. If you consider the work done with the gravitational force, the work done with the gravitational force on the body for motion from A to B will be equal to, as explained earlier about how to calculate the work done with the gravitational force on the body. In general, when center of gravity of the body rises to a vertical height h near the Earth's surface, then the work done with the gravitational force on the body can be done minus mgh if h is very small compared to radius of the Earth. Work done by the gravitational force on the block when it slides back from B to A will be plus mgh. As I discussed earlier, that whenever the center of gravity of the block or body falls through a vertical height h, the work done by the gravitational force of the body will be plus mgh. So total work done by the gravitational force on the body for round trip from A to B and from B to A will be 0. So for the gravity, an example for conservative forces. According to the work energy theorem, the change in the kinetic energy of the body is equal to total work done by all the forces. So change in the kinetic energy of the body when the body completes round trip. That means when the body moves from one position A to another position B, then again travels back to the initial position A. The change in the kinetic energy for round trip means final kinetic energy of the body when it returns to the starting position A minus initial kinetic energy of the body which it had originally at the beginning of the round trip at the position A. According to the work energy theorem, change in the kinetic energy of the body will be equal to the algebraic sum of work done by all the forces acting on the body. Work energy theorem is applicable for all types of examples irrespective of whether the forces are conservative or non-conservative. That means change in the kinetic energy of the body is equal to total work done by all the forces including conservative and non-conservative forces acting on the body. So if the body suppose completes a round trip just under the action of only conservative forces. That means if every force which acts on the body is a conservative force. If the body completes a round trip under action of conservative force or forces only. Of course, some of the problems the body may move only under action of single conservative force. Whereas some of the examples the body may move under the action of two or more number of conservative forces. So if the body completes a round trip under the action of conservative forces only, then work done by each conservative force for round trip will be 0. Then the change in the kinetic energy for round trip will be 0. The change in the kinetic energy when it completes a round trip, that means when the body moves from one position A to another position B, and again comes back to same position A, then we say that you have complete round trip. So change in the kinetic energy for round trip is equal to final kinetic energy when it returns to A minus initial kinetic energy at the beginning of round trip at the same position A. So when the body completes a round trip under action of conservative forces only, then work done by each conservative force for round trip is 0. Therefore, change in the kinetic energy for round trip will be 0. If the change in the kinetic energy for round trip is 0, then the final kinetic energy of the body when it returns to the starting position A will be equal to the initial kinetic energy which it had originally at the beginning of the round trip. That means if a body completes a round trip under the action of conservative forces only, then it returns to the initial position A with the same kinetic energy which it had originally at the beginning of the round trip. Suppose if one of the forces acting on the body is not conservative, That means if the body suppose completes a round trip under the action of a non-conservative force, work done by a non-conservative force for round trip will not be zero. If any one of the forces acting on the body when the body completes round trip is not conservative, if it is non-conservative, then work done by non-conservative force for round trip will not be zero. If the change in the kinetic energy for round trip, if the change in the kinetic energy for complete round trip as it moves from A to B and back to A, if it is not zero, and the final kinetic energy of the body when it returns to the starting position A will be different from the initial kinetic energy of the body which it had at the beginning of the round trip. So the conclusion is that if a body completes a round trip under action of conservative forces only, then it returns to the initial position with the same kinetic energy which it had initially at the beginning of the round trip. But if a non-conservative force acts on the body, then the body returns to the initial position with a different kinetic energy. Considering the same example which I was talking about here, let us consider a block of mass m projected from the bottom of a smooth and fixed inclined plane of some inclination theta to the horizontal. If the inclined plane is smooth and frictionless, then there will be only two forces acting on the block when it completes the round trip on the inclined plane. That means moves from A to B and again flies back to the starting position. That is the gravitational force and the normal reaction force. The normal reaction force on the block by the inclined surface acts perpendicular to the inclined surface, means perpendicular displacement. So work done by normal reaction force, the block will be zero. Work done by the gravitational force of the body when it completes the round trip and returns to its bottom of the inclined plane will also be zero. So change in the kinetic energy of the block when it completes the round trip and returns to the starting position A will be zero. The inclined plane is smooth and frictionless, and if there is no air resistance, then the block returns to the bottom of the inclined plane with the same kinetic energy which it had initially. Suppose if the block is projected from the bottom of the inclined plane with an initial kinetic energy of 3 joules, inclined plane is smooth and fixed, then the kinetic energy of the block will return to the bottom of the inclined plane will be again 3 joules. But suppose if the inclined plane is not smooth, if a frictional force is acting on the block during the motion, then work done by the frictional force of the block when it completes round trip will not be zero. Therefore, change in kinetic energy for round trip will not be zero. The final kinetic energy of the block when it returns to the bottom of the inclined plane will not be same as the initial kinetic energy which it had originally at the bottom of the inclined plane. That means if it is suppose projected up along the smooth and fixed inclined plane in the absence of air resistance, it returns to the bottom with some kinetic energy of 3 joules, for example with a kinetic energy of 3 joules, then it returns to the bottom of the inclined plane with the same kinetic energy of 3 joules. If friction force is present, then kinetic energy of the block when it returns to the bottom of the inclined plane will be less than 3 joules. It will not be 3 joules because work done by the friction for round trip is not zero. As I discussed earlier about how to calculate the work done by the gravitational force on a body, and the body undergoes a vertical displacement h near the earth's surface. Suppose, as I told you, if a body falls to a vertical height h, if the center of gravity of the body falls to a vertical height h near the earth's surface, then work done with the gravitational force of the body will be equal to mgh irrespective of the path followed by the body. If h is very small compared to the radius of the earth, when the work done with the gravitational force of the body, when the body rises through vertical height h near the earth's surface, will be equal to minus mgh irrespective of the path followed. That means work done by the gravitational force of the body when the body is displaced from one position to another position depends only on the vertical height between the two positions and the mass of the body, but does not depend on the actual length of the path or nature of the path along which the body has traveled or moved. So in general, work done by a conservative force acting on a particle when the particle is displaced from one position A to another position B in the conservative field is independent of the path followed by the particle. So work done by a conservative force on a particle when the particle displaced from one position A to another position B is independent of the path followed. It is same for different paths. But work done by non-conservative force depends on the path followed. So if you consider three different paths between same two positions A and B, which you may number them 1, 2, 3. So work done by the conservative force on the particle when it moves along the path 1 will be same as the work done by the conservative force on the particle when it moves along the path 2. Same as the work done by the conservative force on the particle when it is moved along the path 3. Okay, I will continue my discussion in my next class. I will be also showing you the notes for conservative and non-conservative forces in my next class.